Okay, now let's let V1 be this ordered triple, x1, x2, x2 of real numbers. So we could say this is a member of R3, and V2 equal y1, y2, y3 is a member of R3. In the first place, if we add these two, do we get a member of R3? Well, if we add these two, we get an ordered triple, x1 plus y1, x2 plus y2, x3 plus y3. Since all these are real numbers, all those sums are sums of real numbers, so they're all real numbers. So yeah, we get a triple of real numbers. So that this operation of addition of two triples is closed, two triples of real numbers is closed under addition. Now, what would we add to V1 to get V2? Okay, what do you think we'd have to add to x1, x2, x3, the triple, x1, x2, x3, to get the triple y1, y2, y3? Well, whatever we add, let's give it a name. Let's say W is what we're going to add. Okay, then we can write V1 plus W equals V2. Then we could, a little shaky if we do this, but we're going to do it anyway. We could solve this for W. You would think that W would be V2 minus V1. If V1 plus W is V2, then if we subtract V1, we should get W equals V2 minus V1. And we would get then y2 minus x1, y1 minus x1, y2 minus x2, y3 minus x3 triple. And we can verify that that actually works, because now if we add this vector to V1, then we're going to have x1 plus y1 minus x1. Well, that gives us y1. x2 added to y2 minus x2 gives us y2. x3 added to y3 minus x3 gives us y3. So this is the vector which, when added, and I don't know why I put a 1 on that, this is the vector which, when added to V1, gives us V2. Another question, what would you add to V1 to get the 0 vector? Well, let's let W be that vector. V1 plus W equals 0. What would W be? Well, let's let W be the vector with components W1, W2, W3. So we could write this equation as x1, x2, x3 added to w1, w2, w3 equals the vector 0, 0, 0. They're the ordered triple 0, 0, 0. Add these, x1 plus w1, x2 plus w2, x3 plus w3 would have to equal 0, 0, 0, which means that x1 plus w1 has to equal 0. x2 plus w2 has to equal 0. x3 plus w3 has to equal 0. Well, if you think about it for a minute, that means that W1 had better be the negative of x1. Otherwise, you're not going to get 0. So W would be the vector, negative x1, negative x2, negative x3. So there's a vector we could add to the V1 vector to get 0. And that vector we would call the additive inverse. Okay? So that we could say, okay, W equals negative V1. So there's always a vector that we could call negative V1 that's going to add with any vector V1 to give us 0. Okay? Now, another question that I didn't address in class, but let's address it now, is V1 plus what equals V1? Okay, well, V1 plus what equals V1? Well, I'm thinking if V1 is x1, x2, x3 plus some vector, which we might call W1, W2, W3, and that equals x1, x2, x3. Then W1 equals W2 equals W3 equals what? X1 plus what equals X1? 0. X2 plus what equals X2? 0. Okay? So, the answer to our question is the triple of all zeros. Now, there are many formal properties of what we call vector spaces. One of them is that they're closed. If we've got two things that we want to call vectors and add them together, then we want to get something that we want to call a vector. In other words, if we add two members of a vector space, if it's a vector space, then we'd better get another member of the vector space. Okay, well, clearly R2 has this property, and so do many other spaces. We always want to have a zero vector, something which, when added to any vector, leaves that vector unchanged. So, in this case, that was the vector 0, 0, 0. That's our zero vector for the space. Now, you have to read your book to get the whole idea. Then there has to be some vector that will, I'm using W here for the unknown vector. V1 plus some unknown vector equals 0. You always have to be able to add something to a vector in order to get 0, and that thing is called the additive inverse. In this case, it's very simple. If you add negative V1 to V1, you're going to get 0. Now, I haven't formally defined what I mean by negative V1. That means negative 1 times V1. And you have the operation where you multiply a vector by a scalar. And you're going to have to read about that. Then here, I just showed that there's always, for this vector space, there's always a vector that we can add to some other vector to get a given vector. Okay, so if I want to add something to V1 to get V2, I can always find that, and it's going to be V1 minus V2. Now, it's not one of your fundamental properties. It follows from the fundamental properties. There are 10 fundamental properties: closure, commutativity, associativity, etc. And very importantly, the identity property, there are identities, and the inverse property, they're always inverses. Okay? Now, these properties apply just as well, let's say, to 2 by 3 matrices. If I add 2 by 3 matrices, do I get a 2 by 3 matrix? Yeah, well, it's closed under addition. Is there something I could add to any matrix to get that matrix back? Yeah, the matrix full of zeros added to any 2 by 3 matrix of zeros added to 2 by 3 matrix gives you that same matrix. Is there an inverse? Yeah, just, you've got a matrix, change the signs of all the numbers in the matrix, and add the 2, you're going to get the 0 matrix. So you have a 0 matrix, and you have an inverse, additive inverse matrix. All these properties apply. They also apply to polynomials, with some qualifications, to continuous functions, to differentiable functions, and a wide variety of other entities. And they all obey similar properties, so the algebra of all these things is always very similar. And that's profoundly, it's a very profound and powerful idea. That's where we're headed.